Hello everyone, welcome to my presentation called Earth Observation Satellite Data Processing with Pytroll Satpy. I'm Martin and I work at the Swedish Meteorological and Hydrological Institute, and I prepared this presentation with my colleague Gerrit from DWD in Germany. So first of all, what is Pytroll Satpy? Pytroll is a collection of free and open source Python modules for reading, processing and writing Earth observation satellite data. Satpy is an easy-to-use front-end module that is used, for example, to generate imagery or other kind of products derived from lower-level satellite data. Jumping right into the action, we show how we can program in Python using the Satpy library to generate some satellite imagery. The first two lines here are imports that are used later on into the script. The two last lines are gathering first the file names that are relevant to us, and then creating a scene object. The reader used here is AHI-HRIT, which is the format of the files that we're going to work with, and we provide the list of file names that are going to be used. In the second part of the script, we start by calling the load method of the scene object that we created just before in order to generate a true color image. This true color composite is held into the scene object. Then we can call the resample method of the scene object over an area called Japan in order to resample the data, as the name indicates, onto that area. Lastly, we call the save dataset method of the resampled scene object, and we save the true color composite. By default, this will generate a GeoTIFF image that we can then open with our favorite program. The last part of this script is showing three more useful examples of how to use Satpy with your satellite data. The first example is illustrating the usage of the load method that we've seen before, but instead of generating a composite, you are loading single channels. Here, we load the B10 channel and the 0.6 micron channel. As you can see, a channel can be referenced not only by its name, but also by its wavelengths in micrometers. We can also show a channel by using the show method from the scene object. Here, we decide to show the B10 channel, then that will pop up a window on your screen with the data displayed, instead of having to save the image to disk. Lastly, we show how to use the square brackets in a Pythonic way to get the items of the scene object, for example, the channel that we loaded before. These channels, or even composites, are actually data arrays that you can put together using arithmetic operations or perform other kind of operations on them if you want. So, in summary, Satpy is a high-level processing Python module for satellite data. Both geostationary and low Earth orbiting satellites are supported. The indexing of channels can be done by name, by wavelengths, or other properties that can be defined. Many built-in composites are provided out of the box, as well as many input formats and output formats for your data. You can resample the data to any projection that is supported by the Proj library. Now, a question that many of you might have is, can Satpy actually scale up and work in operations or large-scale research projects? Let's see how it looks there. As you probably know, there are new missions coming up in the sky all the time, and we receive much more data than we did a few years ago. Recently, the GO 16 and 17 have been launched and starting producing a lot of data from their ABI instrument. Same thing for Himawari 8 and 9 with the AHI instrument. We have the Sentinels 1, 2, 3, which have granules in order of 10,000 by 10,000 pixels, and of course, the upcoming EPS second generation satellites and the METEOSAT third generation satellites with the FCI instrument on board will produce huge amounts of data that we would like to process operationally. These very large datasets might be problematic in several regards. First, it's too much data to fit in the memory of a regular computer, and that might prevent you from just working with the satellite data that you want on your laptop. Second, it might take a very long time to process because the algorithms are not optimized for parallel processing. As an illustration, you can see the image on the bottom right is an Himawari 8 AHI scene, and it has a very high resolution, as you can see on the left. So how do we mitigate these problems in order to be able to work with the data either interactively or operationally? The first way to mitigate that we have implemented in Satpy is to have an optimized data processing workflow. We use tools that are very efficient in order to increase performance. We use the Python scientific stack with NumPy and SciPy. For resampling, we use PyResample and PyKD3. On the right, you can see a graph showing the performance of PyResample resampling against SciPy and libAn. As you can see, the Pytroll implementation is about 4 times faster than the SciPy counterpart. We use Python geotypepoints for typepoint interpolation. For spectral domain computations, we use PySpectral, and for orbital and space computation, we use PyOrbital. All these tools have been programmed with efficiency in mind. Another aspect of the mitigation is the out-of-memory computations. In order to perform parallel computations in Satpy, we are using the Dask library. Dask provides several aspects that are very interesting for Satpy. The first one is that it allows for lazy processing. Nothing is computed until you actually request the data to be computed. Another aspect that is very nice is the out-of-memory or chunked processing. A full data array is never actually loaded entirely into memory, but small chunks instead are being processed each in its turn. The last aspect that we really like is that it implements the NumPy array interface, which means that if you are familiar with the NumPy array interface, you can use Dask array in a very similar fashion. This sounds all very nice, but let's look at some actual performance results. Before we made the shift to Dask, Satpy was using NumPy with single core processing. To generate an ABI true color image for a full disk, the first execution crashed at 30 minutes just before saving to GeoTIFF. Rerunning it, we were able to have it generate in 23 minutes using disk caching. The peak memory usage was about 103 gigabytes, and the time spent on I/O was 6 minutes and 14 seconds. After we made the shift to Dask, in Satpy 0.9.0 Alpha 1, we were using 8 worker threads. The total time it took to generate the image was 5 minutes and 38 seconds. The peak memory usage was about 12 gigabytes, and the time spent was 3 minutes and 1 second on I/O. The performance boost that is shown in the previous slide was made possible because Dask has a lot of things working parallel out of the box. However, some difficult algorithms are not immediately Dask compatible. So in order to boost things further, we had to make some algorithms Dask compatible. Atmospheric corrections was one of these algorithms we had to adapt to Dask. Resampling is another one. The resampling algorithms are not adapted to Dask yet, but we are making very good progress, and the preliminary results of performance are very encouraging. We hope to bring this to the public in the coming year. The last mitigation I'm going to talk about is the distributed processing. Distributing the load over multiple servers in order to process large data is something that Dask has also built in. Dask provides a small library called distributed that you can use to create a client-server architecture that works automatically on regular Dask code. It works on local machines, on multiple machines, and it works also on clusters. On the right, you can see the results of an experiment we made in order to see how much performance boost we could get through distributed. On the left, we show one server performance. The dark blue bar is showing how long it takes to generate 3 products, while the light blue bar shows it for 1 product. As you can see, the difference is quite significant on one server, but as we increase the number of servers, the difference becomes smaller and smaller. As you can see, there is a nice decrease of the amount of time needed to process those products. However, this is not linear, so it is still very important that things are made efficient for one server in order to run smoothly on multiple servers. Here is an example of how to run Dask on a cluster. You have very good examples in the Dask documentation. You can follow this link and look at it. However, we provide here an example straightly taken from the Dask documentation. As you can see, you can create a local cluster using SSH. So either you use localhost, but you can also use different servers if you have them at hand. Now let's see how all this performs. For testing, we have used 5 different satellites: Sentinel-1 and 2, Himawari-8, MTG, and EPS second generation. The data for FCI and MetImage are of course fake data that we got from EUMETSAT. However, it gives us a good estimate of how it will perform in real life. The performance measurements have been performed on my laptop, which has 8 Intel Core 7 CPUs running at 1.8 GHz and has 32 GB memory. However, for these tests, I have limited the number of cores to be used to 4 to make this more realistic. In the first column, we show the satellite and the instrument that is being used. On the second column, we have computed the estimated data size of the input product. So for Sentinel-1, for example, we counted about 850 megabytes of data that is used for generating the composites mentioned in the next column. As you can see, we are running Satpy to generate the composites, and we use TrueColor for all the satellites except for Sentinel-1, of course, which does not have the channels for this. The next column shows the wall clock time that is needed to generate the composite. And the last column is showing the mean CPU usage and the peak memory usage that is required to generate the composite and save it to disk. One thing to note is that the time needed and the memory usage needed to generate multiple composites instead of just one is not proportional to the number of composites. Indeed, Satpy is very clever and reuses the channels that have already been processed in other composites to generate new composites. So with this, we believe that Satpy is ready for operational and scientific use, as it uses very reasonable time and memory. On the last part of this talk, I would like to give you a glimpse of the Pytroll philosophy and how the Pytroll community is thriving. To sum up, Pytroll is free and open source software. We use GPL for most of the code, LGPL for others, and is hosted on GitHub. All the source code of all the Pytroll packages is available for free, openly on the internet. Pytroll leans toward agile development. We use continuous integration, code reviews, clean coding. We have an active community. We have more than 100 contributors and we run biannual hackathons. As you can see on the graph below, all the indicators are good. This active community is also very welcoming. So I would really encourage you to contact us if you are interested in our work, and we will be delighted to show you around and help you get started with Satpy or Pytroll. Last but not least, I'd like to mention that Pytroll is used in research. High quality of data processing is given by having experts from the community contributing to the software development. Results are reproducible thanks to open source, and reliability is provided by well-tested code. And finally, the openly accessible version control provided by having the code on GitHub makes the software traceable. All these factors make for a successful Earth observation data processing framework for research. Here are some links where you can get in touch with us. We're on Slack, GitHub, Google Groups, and Twitter. Thank you very much for your attention, and I hope to see you soon online.